All right, thank you everyone for coming. So I'm Brad Sond, and I'm going to be presenting my thesis, Leaf Representations with Planning with Contact Uncertainty. So I've been fortunate to work with lots of different robots throughout my career, and so far. And then as you can see, I like getting up close with the robots. And I also like having the robots interact with the environment, both by poking and like looking into tight spaces. Most robots in the world don't do that. Most robots in the world are contained in these cells to prevent people from getting close. Because if the robot crashes into something or someone, it will break it. Fortunately, there's a demand for collaborative robots that can work with people. And that's led to the development of hardware that can sense contact and actually stop before damage occurs. These are great developments. And these videos really show off the sensing capabilities of these robots. But I suspect most contacts don't look quite as clean as this. Most contacts look something a bit more like this. The robot's off doing its thing. The camera's not focused on the contact because that's not the point of the experiment. But then right there, the robot just bumped and the entire experiment has to stop. And you can see the researcher has to come and fix the robot. Now, first, I want to thank my colleagues for sharing this video because we generally don't like sharing videos of robots not working, even though that's most of the time is our robots aren't doing what we want. So my research is really motivated by, we should be learning from this contact. So I want to address the question, how can robots use sensed, unexpected contact information in order to understand the environment? There'll be 4 parts to this talk with 3 major ideas. The first is, what do we learn from contact? How do we model the contact uncertainty? Next is, how do we plan with this contact uncertainty? What types of planners work well? This is going to end in formulating a formal problem for expressing this challenge. What we'll find at the end of this is there are many methods we can use to plan, but also important are the priors that we bring to the problem. As people, we learn so much, we understand so much about the world because we have an expectation of what we should see. So that's the second half, is looking at shape priors. First, we're just going to look at shape priors from vision. What do we expect to see in the world, even with only a partial input? And then the final section is going to tie this together and bring in visual priors, but also bring in this contact information in order to get a better understanding of the world. To start out, I'll be talking about what we learned from contact uncertainty. To motivate this, why do we even need to worry about contact in the first place when we have cameras? We have pretty good, rich data about the world, and it actually, this looks pretty good. But let's look at it from a different angle. And you can see there are several problems. One is that we have some points that are just kind of made up, but we also have large occluded regions. If we look at the picture, it's not completing the picture. Then also if we look at the robot, the pixels of the robot, the voxels of the robot are not quite aligned to where the robot thinks it is. So there's some calibration error. All these small errors will add up and means that there's a good chance we'll end up contacting something when we try to interact with the world. I'm going to introduce focus on a couple canonical tasks. This first one, we're going to be trying to place this pitcher into this bin. The robot doesn't see everything. It sees this single view. And importantly, it doesn't see the side of the bin. So when we look at what does the robot know about the world? Well, it knows where its arm is. That's the green. It knows where the rest of the robot is. That's some of the black. Then it also sees some of its world through the point cloud. But there's a lot of unknown space as well. In our problem, we're going to assume that the robot's not aware of all the obstacles. I'm also going to assume that robots are static, and I'll address this again at the end of the presentation. Unlike many problems, contact will be allowed, and we're going to sense that using joint torques. We expect the robot will bump around a lot because it doesn't see all the obstacles. And that's okay, but we want to use this contact information in order to reach some goal. This section will introduce the collision hypothesis sets method for understanding this contact uncertainty. Then I'm also going to briefly go over a method that we could use, a first pass method at planning and control with these collision hypothesis sets. It might seem that we shouldn't have any uncertainty, that we should be able to figure out the precise contact point. We have this beautiful manipulator equation that we should, it seems like if we just adjust things rightly, maybe we can figure out the specific contact point. That's not always the case. So in some cases, there's just mathematical ambiguity. There's no way to figure out the contact point. Consider a robot arm that swings and hits this post. Well, the torques on the robot look identical, no matter which of these configurations it hits. I think probably even more relevant, though, is their sensor noise. Even though all these positions might make a slightly different torque between the two joints here, the torques will be pretty close, so it's sometimes hard to disambiguate the precise contact point. Now, one way to overcome this is crash into things going quickly and with a lot of force. I'm going for the opposite method, and I want to contact things basically at the sensor limit, basically just where we just notice that we're making contact. Other ways we maybe could find the contact point are through motions of the robot, and this has similar problems to what I just mentioned. We could equip a robot with tactile skin, and we end up learning a lot through the world through our skin. But skin for robots is not nearly as developed. It's going to be costly, and if we end up picking up objects and bumping into the world with these objects, they will not have skin to tell us stuff about the world. Finally, we could assume specific structure of some of the shapes in the world and try to poke them with specific points. For example, we could have touch probes. This is a method to know the contact point, but it is somewhat limiting. So I'm going to assume that contact locations are uncertain, and we're not going to have object models yet. What we actually learn, I call a collision hypothesis set. Consider a robot arm following this path that swings up and collides with this box obstacle. We can detect the torque by looking at, we can detect the collision by looking at the torque. We have the measurements from the sensors, and we have some expected torque from our robot model. When this external torque exceeds a threshold, we call that a collision. Any link downstream of the collision, of the sensed torque, could be the cause of the contact. So in this case, it's the red area in this figure. The possible locations of contact we compute by looking at the next configuration that the robot could be in for all the links that could possibly be in contact. But then we also know a lot of areas that are known free. So all the blue, the robot has already swept through and is already marked as free space. So those cannot be the contact point. Later on, if the robot keeps moving, it might sweep out more free space. And that means we can shrink these collision hypothesis sets and actually get more certain about the contact point. Finally, as a detail, I'm going to store these points in a voxel grid. A first pass we might use for planning is put all of these collision hypothesis sets into a single grid and just basically try to avoid the most red, or most overlap between the different sets. This loses an important piece of information, though, that each collision was caused by at least one occupied voxel. By combining them, we end up losing some information. Consider this case where we have two collision hypothesis sets. Well, both of these scenarios, the arm covers the same amount of red. But so if we use the unified cross-cutter approach, they have the same probability of collision. But if we remember the information that each of these sets was caused by a single collision, well, now we know that there has to be one point in each of these collision hypothesis sets that was occupied. So if we assume kind of that it's uniformly distributed, on the left, there's maybe a 50% chance for each occupied that will intersect with each collision hypothesis set. But there's still some chance that that configuration is free. Where on the right, there's no chance that configuration is free. So that's a subtle difference between actually storing these sets as separate entities. Mathematically, we can calculate this by, if we want to look at the probability that a path collides, we can look at the swept volume of the path and ask what fraction of each collision hypothesis set intersects with that swept path. Then we do some math to manipulate the probabilities to create a total probability that the path doesn't collide given all of the previous contacts. So I just want to point out this is, like, there are assumptions baked in here. And in particular, it's an optimistic assumption. We're assuming that unknown space is free, at least until we encounter a contact. And then we're also assuming kind of the minimum occupancy of each of these collision hypothesis sets. So these assumptions, I think, are a great starting point, and they encourage exploration. As I'll talk about later, it'd be much better to have better priors over the world, but this is a good kind of know-nothing start. What we'll see is our robot kind of bumping around, creating these collision hypothesis sets, building them up. And if we're trying to get through this path, well, we need to somehow avoid a lot of the contacts they already know. If we're only trying to avoid the most red, we might choose a path like this. However, we know that that would definitely collide. So we hope that our method is going to sneak through the middle there because it recognizes that that path has some chance of success. There's a lot of details with the planner that I'm going to gloss over because I'm going to talk about planning a lot more in the next session. But for the moment, a major challenge with planning is most planners would like to treat the total path cost as accumulation of independent edge costs. What I mean by that is if we have some path here, I would like to just be able to consider the cost of each individual, maybe configuration or pairs of configurations, and compute a total cost from that. However, that's not the case, and that means that we can't use many of the common planning algorithms, at least not with making further approximations. There are two reasons for this. One is that we might undercount. So on the left, we have a path, and if we consider each individual configuration, well, any individual configuration could be valid, but we consider the path as a whole, it definitely will collide. So by considering configurations separately, we're undercounting. We also might overcount. Consider now the scenario on the right. Well, each configuration looks like it's overlapping with some of the collision hypothesis set, but it's all the same part. So if the last configuration is valid, then all of them are going to be valid. We would, by adding them together or combining them, we would be overcounting the probability of collision. This leads to a lot of challenges with planning because we don't have the Markov property that a lot of planners rely on. So ideally, we would compute the full path cost for every path we're considering, but that ends up being really expensive. So instead, for this first pass, I'm going to make an approximation and compute small segments and try to combine these segments separately. This makes it more efficient. This is a big balance between finding paths that have low probability of collision versus finding paths in a reasonable amount of time. I'm also going to introduce a controller. And so the full algorithm is basically going to be when we're not at the goal, we're going to invoke our planner, and we're going to try to execute that path. We might succeed, and then we're done. But if we don't, we add a collision hypothesis set. And then we have to invoke our controller. So as long as we're not stuck, we're going to use our controller to compute a path of a short motion. We're going to try to execute that. And we're going to keep bumping into things and adding more and more of these collision hypothesis sets until we decide the controller's stuck or we reach our goal. The controller is pretty simple. If we are at one point, we're trying to reach a goal, we consider a bunch of motions that make progress towards the goal. And we just select the motion that has the least probability of collision. If the best motion is still too likely to collide, then that's when we revert back to our global planner. Okay, so that's a high-level description of the algorithms. Let's actually watch what they do. So on the left, our baseline version, we had to invoke the global planner. And you can see the robot is, in its mind, considering a bunch of different motions, a bunch of different paths to reach the goal. So and then it eventually is able to get there. In the second example, we're trying to reach into this small slit. So the robot's bumping around, adding these collision hypothesis sets. And again, we find that the baseline, using a unified cost grid approach, we have to invoke the global planner a lot more. When we use these separate collision hypothesis sets, we're able to kind of sneak through these narrow passages because we don't block them. In this third example, the robot sees a table, but I've enforced that there's some error here. There's some calibration error, and the table is slightly further away than the robot thinks. So the robot thought that this motion would be good, but it actually does collide. And we end up colliding, but we add these collision hypothesis sets, and our planner avoids them. Our planner and controller both try to avoid them. And so the robot kind of bumps and falls its way around the side of the table until it's able to get above. And then this final one, we're trying to reach into a narrow passage. Now, the robot doesn't know anything about the table. It just has a goal configuration down in that little, in that opening. So it's bumping, it's building up its belief of the world, its collision hypothesis sets. And if we use this unified approach, this unified cost grid, we've now added too much red exactly where we want to go. We kind of have these overlapping sets. And so the robot is now stuck. It thinks that it can't get to the goal. Grab a drink of water. if instead we use the collision hypothesis sets approach. So we've blocked the path to the goal. If instead we use the collision hypothesis approach, initially it looks similar, and the robot's moving around, bumping into things, building up these sets. But even though we make the same, very similar two contacts on the sides, by storing it as this representation, we recognize there is some chance that it can make it through the middle, so the robot's able to reach the goal. So overall, the collision hypothesis sets is able to improve the planning uncertainty, and it's because of this optimism of assuming that potentially occupied regions are free. Now, there is another way that I can use more information in order to do this planning. I want to be clear, this work here was not my creation. I implemented it and applied it to the method, and I'll be showing it off later throughout the talk. But suppose that instead we knew what the object geometry looked like. Well, a contact gives us the same information, that there's some point occupied on the robot surface, but now we can use that to update our estimates of the pose of objects. So by doing this, we're not going to have a much more precise estimate of what the environment looks like. And again, when we go through free space, we can then eliminate particles that are inconsistent with this observation. So this would be an alternative method of modeling the contact information if we knew the object geometry. So this leads us to a method that we combine the two approaches. So the manifold particle filter has a rich prior because it knows the specifics of the object geometry. The collision hypothesis sets is on the other end. It knows nothing about the world. It's assuming everything's free. So I can combine these into a mixture of experts approach basically by weighting the two methods, and we can kind of choose between them. You'll see some examples of that in the next session. So now that I've explained the contact information, what does the robot learn from contact? I'm going to move on to how can we efficiently plan with this contact uncertainty. The problem formulation that I create, I call the blindfolded travelers problem. Again, we're going to have the robot moving around, bumping into things, generating these regions, these collision hypothesis sets of possible occupancy, and the robot is attempting to reach a goal. This is related to a lot of planning and just in trying to avoid collisions. A lot of this work, is focused on avoiding collisions, but it doesn't really capture my underlying problem and doesn't incorporate the information that we gain from a contact. So, and another approach is that we could use is interleaving planning control, which I talked about in the last section. But again, it's missing the kind of, it's not capturing what we truly want to solve here. I'm going to be bringing in work from robotic motion planning, particularly planning on roadmaps, leaf space planning, and then also replanning, as well as work from just general planning under uncertainty, and in particular, partially observable Markov decision processes, or POMDPs. And this problem is actually really related to something called the Canadian travelers problem, which I'd never heard of until I started looking into this. All these things combined to create the blindfolded travelers problem. We have a start and a goal, and we're trying to find a path through this space to reach the goal. I'm going to impose a roadmap. Basically, I'm going to restrict the robot motions to only be on this graph. Now, this is a restriction that, in some ways limits the robot motion, but we can generally find good paths still. And it makes the problem analysis and much easier and allows us to apply many more methods, or many different sets of methods. In classical motion planning, we know where the objects are. So on a roadmap, we can just look at the edges and eliminate edges that are in collision and find a path. In our problem, we don't know where the objects are, and we have a belief over these objects. So we can't necessarily know if a path is going to succeed or not until we try it. We can consider a path, attempt executing it, and we might collide. If we collide, we definitely learn that that path was invalid, but we also learn things about the objects themselves, and it can infer that other edges may be valid or free. We can then replan and find a new path to the goal. Formally, I define a graph with vertices, edges, and edge weights. Edge weights are just going to be basically distance the robot has to travel. And we also need to know, is the edge valid given the true obstacles? And how far we can traverse that edge until we collide. The robot doesn't know these exactly, but instead the robot has a belief over this edge validity and this blockage, how long we can travel until collision. It's going to refine this belief given the contact observations. And the solution is going to be a policy that takes in all this information and outputs which edge the robot should attempt to traverse next. The best solution is going to minimize the expected cost until we reach the goal, given the belief over the over all the edges and the obstacles. So given this problem, we can think of it, we might first just try a couple of methods of tackling it. So here, we have a robot that's going to try edges, some might succeed, but some might fail. We're going to bump and move around and eventually reach the goal. As a first attempt, let's look at optimism in the face of uncertainty. So that is simply, let's find the shortest path to the goal that could possibly work. And let's take the first edge on that and keep following this over and over again. Well, here's an example where that's maybe not the best approach. We do end up reaching the goal, but we end up trapped for a long time in the corner because even there was just some chance that that path could work, even if it was very small. We can get a bit better by instead doing rollout policies. Basically, we can sample a potential world, simulate next actions, and then follow a policy until we reach the goal. This can get us better approaches, but better actions, but still, we can't look that far ahead using this approach. And the farther we look ahead, the more computationally expensive it is. Finally, we might consider QMDP, which at a high level is saying, let's sample a world and let's look at next possible actions. But let's make the assumption that the uncertainty disappears after our next action. And this makes the planning efficient because it's much easier to plan in a concrete world than a belief over worlds. But again, we have these traps where the robot can end up stuck just kind of going back and forth. In this case, the robot could go back and forth between V1 and V2 because it's unsure which path can get us to the goal, and it's relying on that uncertainty disappearing. So my proposed method, again, is just going to be a heuristic. It's not going to solve the full problem. And it's actually, I think, pretty simple. It's avoid the most red. Okay, it's a bit more detailed than that. It's okay. So formally, what we're going to do is I'm going to add cost to the edges based on the probability of collision. So if an edge is likely valid, in fact, if we know it's valid, I'm using log probability here. So we actually add no extra cost, and the edge weight stays the same. If instead we know the edge is invalid, then with probability 1, it's in collision, and we add an infinite cost, and the robot will never attempt that edge. The biggest benefit of this approach, it is very efficient to plan because we're planning over a concrete graph. There's still traps here. This is not always going to find the optimal policy. In particular, consider if one of these edges is blocked, but we don't know which one. Well, my method here, this heuristic, will not assign an infinite cost to this path. It'll assign a larger cost, but it still might be less than the true best path, in this case, the upper arc. So the true optimal policy would know that, whereas mine doesn't reason about that. And that's the same thing as saying, again, that this method isn't obeying the Markov property, or is pretending we have the Markov property when we actually don't. However, because we've imposed the blindfolded travelers problem, where we have this graph with relatively large edges, for this specific problem, it ends up not being as big of an issue, because in general, edges are not as tightly coupled as with the previous approach. So all of these methods have traps that we've looked at so far. So we can ask, is there a method that doesn't have any traps? Is there a true optimal method? And the answer is no, and I can prove that this problem is in fact NP complete. I'm going to skip that proof for this. However, if anyone is interested, I like thinking about it, so feel free to talk to me afterwards. But instead, I'm going to show videos of the robot working on. We try a bunch of different strategies. We have the belief methods I've talked about on various environments. So here you can see both the manifold particle filter and the collision hypothesis sets working together. So we have a belief over where the table is, so those are the red planes. And as we bump around and move around, this belief gets more and more compressed and more accurate. And we also have these lingering collision hypothesis sets that, that provide a different source of information to help us reach the goal. When I compare numerically across all these methods, there are some clear losers. There's maybe a couple methods perform fairly similarly. The biggest takeaway though, however, is the improvement over this baseline, which is the method that I talked about in the first section. Our first path attempt at planning resulted in a planner that worked, but the blindfolded traveler's problem and the corresponding solutions have made this planning problem much faster. Or another way is we can say this is we can tackle much harder problems now. Let me bring up a kind of a maybe odd example, but I think it actually occurs quite often. Suppose we have a robot in this environment, and there is truly a table in front of it, but we haven't told it about the table. The robot knows about a chair in the corner of the room. That's the chair on the side, but it doesn't actually know about the table in front of it. Now, at first, like that seems weird. Like, why doesn't the robot know about the table? In my experience, though, I think this happens quite often. Is that the robot is missing a piece of information, and if we're too confident too confident about our information, then there's just no way to recover. So what you'll see is as we bump the first time, we have to explain that contact with the chair. But very quickly, we realize that it's impossible to explain with the chair. By using the mixture of excerpts approach, we at least have the collision hypothesis sets to fall back upon. So it's not as efficient, but we at least have something to guide our belief of obstacles. So we can still, in this case, attempt edges and reach our goal. All right, so that summarizes the planning approach. But we're left with two belief models, both of which have limitations. The collision hypothesis sets assumes unknown space is free, and the particles requires this knowledge of the specific object shape before we can do planning. And that restricts the types of environments we can operate in. Collision hypothesis doesn't have enough information, and the particle approach requires too much specificity. The remainder of the talk is going to be focused on shape priors. At first, I'm going to look at shape priors just from vision, and then I'm going to bring the contact information along with the vision in order to create good estimates of the types of objects that we might see in this world. Consider that we see a mug on the table, but we only see the mug from the front. I use a segmentation algorithm to segment out the mug from the rest of the objects in the room. And then I have the 2.5D input grade points of the mug. I don't know where the handle is, but I would like to complete different mugs that show the handle in different places that capture the uncertainty that I have about where the mug handle is. I could use shape matching, or I could do something that's been popular very recently, shape completion. That's taking a neural network and feeding the information through a network to try to complete the shapes. As input, this might take voxels, points, depth images, raw images, and as output, we can get similar diversity in representation types. Both take voxels, and that's what I'm going to be using in this case. And then we have different loss functions, basically just different ways to evaluate how good we are doing. Shape matching can get us very good matches, but again, it requires these specific models. So if I want to remove my dependence on these models, I'm going to move it to shape completion. The existing work on shape completion really focused on creating the best single object, but didn't care about really capturing this diverse belief of possible objects in ambiguous cases. In all the videos, you'll see a ground truth, the 2.5D from the camera, the completions from the network, and you'll see plausible completions. So these are completions which I've decided represent the uncertainty that I want. When the handle is occluded, I want to see diversity in the plausible completions and the completions from the network. When the handle is visible, I want to see much less diversity because there's much less uncertainty about the true shape. The plausible shape I construct in a classical way, not using a neural network. Here I have the 2.5D view that the robot sees, and I take a bunch of different shapes from a large data set. And I try to match these shapes to the points that I see, using iterative closest point in this case. And that gives me a shape that is at least matched to the points that I see. I then compare the depth image that I observe, the depth image that I would observe if the shape were the shape that I'm in the world. So I reject any that produce depth images that are too different. And this leaves me with a plausible set. From my data set, of these shapes have similar enough depth images that I think, yeah, they could be the shape that I'm seeing in the scene. To evaluate my method, I create this plausible diversity metric. This has two components. First is the plausibility, and that asks for each shape sampled from the network, I want to find the nearest plausible shape that from my plausible set. So you can see I just iterate through all the plausible shapes and look for the closest. The mirror of that is coverage. For each plausible shape, I also want to have generated shape that is close. In this case, I'm using the chamfer distance metric. Combining the two, I end up with a plausible diversity metric. So I want to create shapes that are both plausible. They might appear in the scene, but it also captures the diversity of the shapes that I might expect. I'm first going to be looking at mugs from ShapeNet, and I take all the mugs, rotate them around. I also have this bounding box information. So I create a bounding box aside. The bounding box also rotates with the shape. For the method, first I'm going to construct a normalizing flow to model this bounding box. There are lots of details here that aren't that important to understand. Basically, I have some mapping between bounding box and some latent space. With this, I can then sample latent boxes and pass them back through the flow. And that gives me box-like structures. So far, I can create boxes, but that doesn't seem all that useful yet. The actual shape sampling network is going to be structured as an autoencoder, where I take the 2.5D input, the known free space, and I use an encoder to convert to create a latent vector. I can then, it's a latent mean and variance. I can then sample from this latent variance, pass this to a decoder, and create a 3D shape. This creates pretty good looking shapes when there's no ambiguity. The problem is if there is ambiguity, it's really hard to make the network pick a specific shape. You really narrow down a specific shape. There are several approaches that I've tried, and it's just really hard to get it narrowed down to a single shape. The approach that I ended up on is forcing the latent vector to represent something specific, at least forcing a portion of it. So I enforce that the encoder predict that part of this latent vector represents this bounding box information. During training only, during the decoder, I replace this portion of the latent vector with the true box. So this removes some ambiguity from the decoder. This basically forces the encoder to handle the ambiguity portion when it creates its latent space uncertainty. But the decoder can then be much more specific in constructing good-looking, very specific shapes. It removes some of the ambiguity from the decoder. What this looks like in practice is when we complete shapes, when the handle is visible, multiple methods look pretty similar. Ours in the upper left, maybe jittering around a bit more, but they all look pretty similar. The real key comes when the handle is occluded or when there's ambiguity. So watch now, our method is producing all sorts of different handles, where the other methods weren't really reconstructing handles that well at all. So qualitatively, this looks much better, but also quantitatively, evaluated on the plausible diversity metric, we find that ours creates the best plausible diversity. I've also run this with YCB objects. That's a data set of tabletop objects. And I've also added slit occlusion here. Basically, the robot can't see the entire object, it only sees a small slice. And again, we see that our network produces a variety of different shapes, and these correspond to the plausible diverse, the diverse set, the plausible set that I created as well. With the other methods, there's maybe some variation, but not a whole lot, and it's not capturing the diverse range of shapes. This diversity can be important when we're trying to complete tasks with robots. So here, the robot sees a mug. Again, we're going to segment the mug from the rest of the world. And we can complete these shapes. Now, it doesn't look as good with real data. With live data, there's more noise. But I can still construct a pretty basic algorithm that tries to detect the handle. And we're going to try to pick up the mug by the handle. In ours, we capture a lot of the diversity. So when you go to grab, we're successful. Where in the baseline, it had a wrong belief where the handle was and wasn't able to grab it. In the second example, we're trying to pick up a Cheez-It box, but we only see this very small sliver. Since the network has been trained on YCB objects, it's recognized this and is going to create YCB objects as its output. It doesn't know necessarily that this is a Jesus box. Multiple things could match to this, but our method creates a large, diverse set of points, and the baseline is very confident in the wrong object. So when we go to grasp, our robot chooses a grasp that will work for all, or as many as possible of these diverse shapes. Whereas the baseline incorrectly was overconfident about the wrong object, and so it did not succeed. So that's a basic level of how we can use the diversity. But even in the baseline case, we collided and we failed. So I would like to use that information to then update our model. And that brings us to the last section of using contact and visual informed priors. So back to our case, if we're looking at mugs in the world and our robot moves around, well, if it's nowhere near the mug, we probably wouldn't expect anything to update. But once we actually collide right there with the mug, I want to update the shapes so that they all have portions that explain that contact. I really like these figures watching the handles kind of tip up in order to explain the contact. One way of thinking about this is we start out with a large diversity of objects from vision only. There's a lot of ambiguity. But as we make contacts, the world should collapse. The beliefs of the world should collapse and become more and more crisp, more and more a single world. I'm going to explain our method using a baseline shape where I'm just going to complete boxes. So if we just want to complete boxes, there are probably other ways to do this. This is mainly for illustration. So we have a ground truth box with the black voxels there, and we can sample from our network, and that generates this diverse set of boxes. This is great because I don't actually know the depth, and I'm getting diversity in depth. As the robot moves, we sweep out from some free space. And so far for most of the boxes, that doesn't actually matter. So we're not going to have any penalty or there isn't any problem with those. But for some, the box now collides with known free space. I'm going to use this information and construct a loss and use gradient descent in the latent space shape in order to improve my end shape so that it is not going to violate this free space constraint. Separately, if the robot moves and collides, that introduces a new constraint. We now have a loss function on occupied space. So the robot's collided. We need some explanation of the shape that explains this collision. I do the same gradient descent process optimizing this loss. Not all of them succeed. So this gradient descent procedure sometimes generates shapes that don't violate the constraints, but that's fine. I can just reject these samples. As long as a decent fraction of them succeed, then I can create a decent belief over possible shapes. The final term of the loss function enforces that the final shape, or the latent shape, agrees with the visual prior. If we didn't have this constraint, then as we're doing this gradient descent, we could diverge pretty far from original information and end up with shapes that maybe satisfy the other constraints, but aren't reasonable given what we actually see. One way to think about this is that we're projecting these points onto the constraints. So given these ovals, which represent level sets of the Gaussian prior, we can sample some black points and use this gradient descent optimization procedure to move onto the contact manifold. Loss functions have three components. So the free space loss just says of the space, for each voxel, if we know it's free, but we don't predict that it's free, then there's some loss term there. Separately, we can bring in the collision hypothesis sets for points that we know that are in contact. If we don't predict a point in contact, then we suffer some loss. And then the final term just says our sample should be likely given the encoder, given the image, and then the encoder applied to that image. When we apply this on real boxes or real objects, we again use a segmentation algorithm to focus on the object that we were most interested in, or the objects. And as you can see, right, the segmentation of visual data, I mean, it's not perfect, and that also means that our completions are going to have some errors in them. But as the robot moves and then contacts the object, right there, we made contact. We then update the shapes using this procedure. And you can see they grow in to fill up the occupied space, and not just the collision hypothesis set. The entire shape changes, and actually, and looks maybe not visually exactly like the Cheez-It boxes, but in terms of occupancy, it ends up being pretty close, which is the important thing for planning. Here we see the same procedure on this picture, and our completions are, they're maybe not bad at the beginning, but you have some that are missing some space. So our first motion, the robot didn't contact, so we just swept out free space. But next we make a contact, and now the remaining shapes have to grow to explain this contact. We can look at these results numerically, and on the y-axis, I'm comparing distance to the ground truth object in the scene. There's a lot of data here because I compare against ablations of the method as well as other approaches. The key takeaway, though, what I think is most important, is that as we make more of these observations, our estimates of the shape improves. So we're using that contact information in order to better understand the world. I compare this across a lot of different, across several different shapes, both in simulation and the live robots. All right, so backing up to the big picture, I've explained a framework for planning using context uncertainty. The first step is understanding the observations. What do we actually learn from making the contact? That was the collision hypothesis sets. Those are used to understand our belief over environments. That's what I've talked about most recently, as well as there are several methods for doing this, but including using these neural networks to have a prior over shapes. This in turn feeds our belief space planning approach, where we plan over our belief of possible environments. We then get an action to execute, and that might get us to our goal, or we might have to continue this, getting another observation and continuing this loop. I presented this framework, and I hope that it ends up being useful, but I don't mean to imply that the problem is completely solved. In particular, I want to identify 3 areas that I think are ripe for improvement. The first is I've assumed static obstacles, which may be fine if we're bumping into things like refrigerators, but probably not if we're bumping into lightweight objects on a table. Fortunately, a method for handling this fits in very nicely with the approach I've used. So I've used particle filters often to model these objects, and they have an observation model that takes a state and an observation and gives us an updated state. But there's another part of a particle filter that I've mostly ignored, and that's the motion model, which takes a state and an action and creates a new state. This conceptually is very easy to slide in. The hard part is actually figuring out how objects move, especially when we don't know their weight or their exact shape. Fortunately, I have other lab members, other colleagues who are working on this problem. So hopefully one day that will be able to fit into these methods. The second is leaving the graph. So I've mentioned the benefits of planning on the graph, but it does lead to some unintuitive behavior. So if we make a contact, we might not want to back up. We might want to kind of be like a bug and traverse the side of this object. That would look like adding a bunch of different nodes to the side as we traverse around. I've looked into this in terms of like using a controller to kind of hug the sides of objects, and it's fairly difficult. You have one problem is that we don't even know where the contact point is, but also maintaining the contact is hard. And we also don't want to add too many nodes, so we just kind of create a bunch of nodes, but that's not actually helpful for our planning problem. The final area of extension I want to mention is finding the goal. Originally, I've assumed that I know where the goal point is, which is a little bit odd when I don't assume that I know all the objects in the environment. My framework did look like we have a belief over states that leads to planning, leads to execution, and then back to observations. But I've added in a module that explains this belief over goals. I've actually snuck it in at the end without telling you, but during this last section where we are bumping into these Cheez-It boxes, the actual goal state is dependent on the shape completion. So my way of designing the goal state right now is fairly naive. I mean, it can be any function, but I think this is a real open challenge in robots is when we just get to an unknown environment, not even before even doing the planning, just deciding what even is our goal is an open challenge. So I look forward to improvements in those areas. I don't know how to learn without talking with a lot of other people and learning from other people. And I've had a great opportunity in this lab. So I want to thank everyone in my lab. And I want to thank my committee and also especially Dimitri. So I came in 4 years ago and I can look back and just realize how much I've learned in these 4 years. And there's way too much to mention. I think to choose one specific that Dimitri has really taught me well is how to approach a nebulous problem and step back from all the details of implementation and really decide what is the true problem that I want to solve. Now, that problem is almost certainly way too hard to solve. So then explicitly enumerate the approximations and assumptions that I need in order to solve the problem. That's been a real help. And then 6 months ago, you've all probably heard now my baby Kevin, who is already better at manipulating objects than many robots. So unfortunately, fortunately for me, there's a lot of work left to do in robotics. A lot of open research. I've had the opportunity to do a lot of work that I haven't mentioned here. And in particular, if anyone's around in the next month and wants to play with a robot in virtual reality, please stop by the lab because I love showing off. So with that, I'll open up for any questions.